Today we're going to be talking about what is possibly the most simple topic, actually is the most simple topic you are ever going to talk about in chemistry, yet it's going to be a little confusing. So why would that be? Because we're going to be talking about the subatomic structure, which takes you all the way down to electrons, protons, neutrons, everything, the most basic elements of what makes us up. Or in other words, the most simple elements. But they're not quite all that simple. There's a lot of rules that govern them. So that's going to be what we go over right now. When you're looking at the atom, we look at it from a nuclear structure right now, which is to say that it has a mass of protons and neutrons and a little ball at the center, or sometimes shaped like a football. They're not always perfect. And surrounding those protons and neutrons, you have these orbitals of electrons that kind of float around it. And that gives you your nuclear idea. However, over time, it took people a long time to figure this out, which makes sense considering that you can't see atoms with your bare eyes, or even with normal light microscopes. So, the first model of the atom that came along was Dalton's model of the atom, and it basically had five components. And it said that everything is made of atoms, which makes sense. The Greek term for atom, the idea of the atom was the smallest particle of anything. So if you kept cutting up a piece of bread, eventually you'd hit an atom. Theoretically. So everything's composed of atoms, and atoms cannot be created or destroyed because once you reach the smallest level of small, it can't get any smaller. Again, it makes sense. And atoms are alike in every way. So if you have an atom, atoms of the same element. If you have the atom of the same element, hydrogen will be hydrogen, will be hydrogen, will be hydrogen. It will always perform the same way in chemical reactions. Again, it makes sense. Then atoms of different elements are different. To say a uranium atom will not perform the same as an oxygen atom. Please don't try to breathe them. And atoms can combine together in small numbers or even larger numbers like DNA to form molecules. Okay, so some of it was right. He did pretty good. He did a pretty good job for a basic model of the atom. However, we moved on after that, and Rutherford did some experiments which showed that there are negative charges contained within atoms, and this would be the electrons. This moved on to the more pie pudding method that he proposed, where an atom was a generally positively charged ball balanced by negatively charged pieces floating around in there, which were your negatively charged electrons. We then moved on from that, and we said, okay, there's some other stuff in there too, which would be your protons and neutrons. And this was when we were demonstrating that the majority of an atom was empty space. So you could shoot particles through an atom, and a lot of the time it would end up getting through, which wouldn't be the case if the entire atom was positively charged instead of just a little piece of the atom in the middle. And finally we arrived at this wonderful model, which was Bohr's model, and Bohr said, guess what guys, it's like the solar system. So we've got this wonderful neutron and proton nucleus in the center, and it's this mix, and around those protons and neutrons, connected by electromagnetic forces that keep the electrons pulling in, is this cloud of electrons, and these electrons are arranged into rings, again like the solar system, and then they orbit the nucleus. Then this gives us good theory to work off of. And we're going to be talking about this theory for a little while longer before we take it a little bit more technical and look at how it really works, as scientists say nowadays. Because you could always dig deeper, and we will dig deeper. But for right now, let's think about it as that orbital model. So you have two things when you look at your periodic table that you'll see. First things first, you're going to see an atomic number. The atomic number is like when you say oxygen is 8. If that number, the big one, right above the name of the element. And your atomic number is the number of protons. It's the number of positive charges in your atom. However, there's also the mass number. Why are these separate numbers? Excellent question. The mass number is the weight, or the mass, of your element. So the mass number for a single atom, we're not talking about the average mass right now, just the normal mass is going to be your protons plus neutrons. You might say, what about your electrons? Don't they count too? They don't, because they're so light that they're almost negligible. So when you're talking about typical mass, you're going to say it's just protons plus your neutrons. And the mass number can change for elements of the same species for the same elements, because you have different atoms within the same element group. And unfortunately, Dalton was wrong. They can change. And that's what we have isotopes. An isotope is going to be a particular element, say isotopes of hydrogen. However, you end up having different forms of hydrogen. For example, one might have your typical hydrogen only has one proton and one electron. However, there's forms of hydrogen that have a proton and two neutrons, or one neutron. And by adding or subtracting neutrons, it doesn't change the overall charges, and charges determine the majority of chemical bonding and everything of that, which is going to mean that your atoms aren't going to perform differently. However, they are going to weigh slightly more. So mass number changes between isotopes, atomic number changes between elements. Back to the hydrogen example. Hydrogen, the typical form, is just going to have a mass number of 1. 1 proton, 1 electron. Electron's negligible. 1 times 1 equals 1. However, if you look at the 2 electron for the two particle form, if you're looking at your nucleus having 2 particles for hydrogen, you end up getting a mass number of 2. You have a neutron and a proton. If you have 2 neutrons, mass number 3. Pretty straightforward. There you go. So, and now you know what an isotope is. An isotope is just an element that has a different mass number. And you know what an element is. An element is simply an atom that has the same atomic number as every other atom in its species. Finally, we're going to talk about the last major distinguisher. We'll talk about allotropes later, but don't worry about those right now. And that's going to be ions. An ion is going to have, for all states and purposes, the same atomic number, and is probably going to have the same mass number as well. However, what differentiates an ion is that it's going to have a different charge. And now we're going to be talking adding or subtracting electrons. So you might be tempted to say, well, if we're talking about an ion of helium, typical helium will have 2 protons, 2 protons and 2 electrons, and then a few neutrons in there as well. You might be able to say, well, if we're talking about helium, what if we were to have an ion of helium? Which, by the way, helium doesn't have any ions because it's a noble gas and it doesn't do that. However, in theory, if helium was to have an ion, you're not going to be removing the protons. Because you remove the protons, that changes your atomic number, and that changes the entire behavior of the atom, and at that point it's now hydrogen. What you're going to do is you remove your electrons, or you can add electrons. So if you're taking lithium, for example, lithium has a typical mass, typical atomic number of 3. It's going to have 3 protons, 3 electrons. However, lithium wants to reach a more stable structure. Reaching a more stable structure means having a noble gas electron configuration. What does that mean? Just having the same number of electrons as helium, because remember, helium doesn't react. It's very stable, so other atoms want to achieve that configuration. Lithium, thus, has the tendency to lose a single electron, which will give it just 2 electrons, and when it loses that electron, then it's going to have a positive charge. So you take away a negative charge, and you have 3 protons to only 2 electrons. Do the math, and it's going to be lithium plus. And that's what an ion is. An ion is when an atom loses or gains electrons to then have a different charge than the typical state atom. Because typically an atom will have a charge of 0, and then as you gain or lose electrons, that charge will go up or down. Okay, so now we hinted about this earlier, about the idea of average atomic mass. So the average atomic mass is based off of the idea that A, atomic masses can be measured, and B, because of isotopes, they're going to be different. So the average atomic mass uses the units AMU, average mass units. We'll put something in the video if that was wrong. AMUs, and when you're looking at atomic mass units, there we go. AMUs, the idea is it's simply 1/12 of a carbon-12 atom. 1/12 of a carbon-12 atom, what does that mean? Don't worry. A carbon-12 atom is simply a standardized atom. It's very common. It's the most common isotope of carbon. And it has, it's carbon-12, which means it's going to have 6 neutrons, 6 protons. We take that and we say, well, we take 1/6 of that. It'll give you more or less what the mass of a single neutron or a single proton is. So we scale off of that. And then you go and you're going to be asking, okay, so what is going to be our average atomic mass? An average atomic mass simply is based off AMUs. It's in AMUs, and you take you take an element, say hydrogen, you take all of its isotopes, and you look at their commonness. So if you have your isotope, your original hydrogen, which is going to just be straight up hydrogen, and it's going to have a mass of 1. Then you go up, you're going to have a hydrogen version with a mass of 2, because it's going to have a proton and a neutron, a mass of 3, a proton and 2 neutrons. And if you average all of those with a weighted average, which means if you have 1% of all your atoms being hydrogen 3 and 2% being hydrogen 2, then you say 0.01, because 1%, times the mass of a hydrogen 3 atom, which would be 3, plus 0.02, 2%, times the mass of a hydrogen 2 atom, which would be 2, and then 0.97, again, 97%, that's the rest, because the rest of hydrogen is just straight up hydrogen, times 1, which is the mass of a hydrogen 1 atom, or the typical hydrogen, and add those all together, and that will give you your average atomic mass. And that is the number you see on the mass, as the mass on any periodic table. For example, if you look under carbon, you're going to see 12.01 or 12.011. Why is this? It's because for carbon, yes, 1/12 of a carbon-12 atom is 1, so you would expect it 1 times 12 again, and you get 12. Remember, carbon also has different isotopes. There's carbon-13 and carbon-14, and each of these have some density, and they're going to end up bringing up this number instead of being the normal number. So when you factor those in, that average goes from 12 to 12.01. Next up, we're going to be talking about mass spectra. The idea of mass spectra is that you have this wonderful thing called a mass spectrometer that sorts atoms out by exactly how massive they are. So if you had a sample of hydrogen, and we've been talking about hydrogen a lot, it's nifty. If you have a sample of hydrogen and you put it through a mass spectrometer, you're going to see 3 lines at H1, H2, and H3. And that's because hydrogen's getting split up. So you're going to see the mass of 1, the mass of 2, the mass of 3 for your 3 different isotopes of hydrogen. And doing this, you can then measure the frequency of each isotope. You could do something like this for chlorine as well. Chlorine has 2 isotopes, chlorine-35 and chlorine-37. And when you're looking at that, you're going to get 2 lines. You're going to say there's X amount of chlorine-35, X amount of chlorine-37, and with the mass spectrometer, because what it does is it separates by the atomic mass, it's going to end up giving you your percentages. And then you can use this later on, once you know your frequencies of your different isotopes, if you know your masses of your isotopes themselves, voila, you can use it to go and calculate what exactly your average atomic mass is. Mass spectrometer. Pretty straightforward example. We'll talk about more about this in chapter 11. Now, what we've got to talk about is electron configuration. Electron configuration is the heart of chemistry. Chemistry, we don't really worry about the neutrons. They're neutrons, they're neutral, they don't do much. Then the protons, we worry a little bit about those. Those are going to be able to tell you, what atom you have after all. And they make a big difference. But it's the electrons where you get your real meaty stuff, okay? So we're going to be talking about how exactly the electrons are configured around the atom. And when you're looking at this, we can tell a lot about electrons from the electromagnetic spectrum. And the electromagnetic spectrum is the idea that every electron, when it drops down from an excited energy level to a base energy level, is going to create a particular type of light. A quantized, quantum type of light, because it only is going to produce what? It's dropping a certain distance, produce a certain amount of energy to create a certain color of light. Okay. So you're going to learn shortly later on how you can figure out exactly what the base level of an atom, of an electron is. But for right now, we're going to take one more time, maybe not the last time, but one more time, hydrogen as an example. Let's say hydrogen. Typically, it's got one electron. And an electron that has no extra energy, extra oomph added to it, is going to be hanging around at the base energy level. And that's going to be level 1 for hydrogen, because there's no other electrons for this lone electron to compete with. So it's going to be hanging around there, and level 1, and at the very middle, you've got your 1 proton. We're just going to be taking the H1 isotope. So when you're looking at your H1 isotope, what happens if I were to shine a laser at it? Or more efficiently, I could just shine some UV light at it, because UV is a little higher power. You shine your UV light at it, and what you're going to end up getting is that electron jumping, because it gets extra energy, it gets excited, and energy helps it overcome the electromagnetic force that the nucleus, which is that 1 proton, is pulling on it. So it might jump up to level 4. And when it drops back down to the base level, when it no longer has enough energy to support itself, or if it drops back down to level 2 or 3, that's going to be when you get your light. So these drops allow us to create a spectrum. There's 2 different types of spectrums. There's your standard continuous, there's not that. There's your standard electromagnetic spectrum, and then there's also your emission spectrum. So you have atomic absorption, atomic emission, and this all occurs over the continuous spectrum. The continuous spectrum is just what you expect when you essentially see a rainbow. It's all the colors out there that can be produced. Then what you get is the atomic absorption and emission line spectrums. The absorption line spectrum is what happens if you have gaseous, if you have the gaseous form of an electron, not an electron, of an atom suspended in air, and you throw light through it. And what wavelengths get absorbed by the atoms. Then, on the other hand, emission is what happens when the atoms get excited and they release light. And exactly what wavelengths they release light in will give you that wonderful picture. And by this, using emission line spectrums, you can figure out quite a bit. For example, this was how we figured out the constitution of what types of atoms are present in stars. And we were like, whoa, stars are made of hydrogen. They're just big balls of gas. Nobody really thought of that before, but then after we looked at stars, and we said, wow, their emission line spectrums, the type of light getting produced by a star is the type of light produced by hydrogen when hydrogen burns. Voila, now we know that stars are mostly made out of hydrogens, and hydrogens are made out of protons and electrons. Remember that, kids. Okay, so now we have that idea. When you're looking at this, it gives a lot of credence to the Bohr model. Remember, Bohr's model said we've got a single nucleus and surrounded by orbitals. And that's going to be where your electrons are hanging out, kind of like the solar system. Because it's a spectrum that has single lines, it suggests that there are specialized levels. What I'm saying here is an electron that does not have to be locked into a particular orbit, for example, from orbit 1 to orbit 2, could drop from orbit 2 down to orbit 1.5, and then you would have all colors of light represented by the emission line spectrum of a particular atom. That's not the case, however. When you look at the emission spectrum of hydrogen, for example, you only have 4 lines on there, and that means that there's only 4 possible jumps that the electrons end up making. And this is the proof that we see for Bohr's model, which is saying that the electrons have to jump back down specified distances to produce specified quantifiable amounts of energy and produce particular wavelengths of light. AKA, there are orbits, and these electrons stick to the orbits. They can move between orbits, but they can't move into orbits that are between the orbits. Then we are going to look at the hydrogen spectrum. We were already talking about it a little bit, and the hydrogen spectrum is pretty straightforward. It's got 3 different drops that typically get made, and they're going to be called the Lyman, Balmer, and Paschen series. Now, complicated, right? Yeah, but we can get this figured out. The hydrogen atom, for that, its electrons can only go so high. So you can go up to level 7, and then you come back to the bottom of the ride. So the electrons typically drop down to either levels 1, 2, or 3. When they drop down to levels 3, level 1, we'll start at the bottom, drops down to level 1, it's a long drop. And as you would expect, as a long drop, it's going to have high energy. Think if you dropped a ball off your roof versus dropping a ball off the Empire State Building. Empire State Building, more energy. And because it's more energy, it's going to produce the UV spectrum, and that's going to be your Lyman series. UV light is very intense in power. This is why if you have plants, you can actually use the UV light to help your plants grow. Bonus, now go and grow plants with UV light. The next level is going to be visible light. This is dropping electrons from anywhere above 2 down to level 2. And this is in the middle for energy. Pretty straightforward. It's called the Balmer series, and this will create your wonderful reds, greens, and lots of purples. Purple, purple, purple. Finally, we're going to have the Paschen series, which is your infrared light. This is the lowest energy level, and it's kind of the equivalent of dropping a ball off the kitchen table. It doesn't go very far. Because of this, it's going to mean that infrared light is not very powerful. Just doesn't really do very much. So, there you go. It's going to drop. Big drop equals UV equals Lyman. Medium drop, that's going to be your Balmer, which is visible light. And small drop, Paschen, which is going to be your infrared light. Now, when you're looking at electrons, you can look at them two different ways. We've been talking about the idea of the single electron making a drop, and this lends credence to the idea of the particle theory, that an electron is a single discrete particle. You could say, that's an electron right there, I see it, and it's a particle. However, there's significant evidence, and in several places where electrons act, they act as waves. So we see this duality with electrons, which is that they can act as waves and they can act as particles. If you would like, you could just look up the double slit experiment. I'm not going to explain it in depth here because it's a bit extensive, but the idea is that an electron can act as a wave, which means they can move essentially as a group, and they can act as a particle. They can have a discrete location for a particular minute in time. Now, why does this work out? It's going to come down to the Heisenberg uncertainty principle, which says that because of the nature of an electron, its location and its energy level, or its speed, can never be known at the same time. So if you're looking at an electron, you could say, okay, there was an electron there a second ago, because guess what? By the time you measure it, it's already moved. Or you could say an electron is going to be this high energy level, but if you know how high the energy level is, you won't know where it is. The electron, that is. So what this is saying is that the electrons can essentially move as a group. You don't really know where they are, because when you look at the Schrodinger model, it's saying, just like Schrodinger's cat, it's there and it's not there at the exact same time, because electrons don't really follow the typical rules of physics. They exist and don't exist within an area, we'll talk about that later, called an orbital, at the same time. And this is why it has the properties of a wave. Because when you look at a wave, it's this entire area. You're not looking at a wave as a particular particle. It's a movement. Versus with electrons, they're moving. But at the same time, they can be at a particular energy level. Okay? And it's the very same for light. When you're looking at light, it can come off as a wave because of electrons. But then the electrons themselves can be particles as well. Bonus. So, after Schrodinger models, now we can look at the atomic orbitals. We have the idea that electrons are there and aren't there at the same time. We know they're somewhere. We just don't know where that somewhere is. And that somewhere is going to be within an orbital. The first energy level is the 1s orbital. And the idea of orbitals is that the electrons have a high probability of hanging out in that place at any one time. Which means that I believe it's a 95% probability that the electron will be within the area enclosed by said orbital at any time. They could still be outside the orbital, because electrons don't like to be neat and simple. But probably if an electron is at the first energy level, you're going to say it's going to be at the 1s orbital. The 1s orbital is a orb, a sphere around the nucleus, and electrons will be there. Then an electron, once the 1s orbital has been filled up, will move on to the 2s orbital, which is pretty much the same thing. It's still the S-shaped, the orb, and then it can move on to the 2p orbital. And the p orbitals look kind of like a something. They're odd. You're going to see an image over there of what a p orbital exactly looks like. And the important thing about p orbital that you know is just that there aren't any electrons at the middle of the p orbital at the nucleus, because there's a nucleus at the nucleus, and electrons, remember, are negative. They get pushed away by the protons, so they can't hang out right at the nucleus, and they're kind of hanging out in that infinity sign around the nucleus. There we go. And then D and F orbitals are just really weirdly shaped, so we're not going to go too in depth into how D and F orbitals work. Just know that the electrons hang there and they do their thing. However, because D and F orbitals tend to be slightly lower energy levels than their 1s and than their s and p cousins, what ends up happening is that the s and p cousins create the valence electrons, which are the outer shell electrons, which are most responsible for bonding. So the D and F orbitals are rarely going to have a major effect on how the bonding and thus the chemical behavior of an atom is affected. Okay, so now how do we fill up these orbitals? We know where they are, we know where the electrons are going to go. There's a few rules to help us out. First things first, we have the idea of electron spin. Any orbital can be filled by 2 electrons, and the electrons have to be spinning in opposite direction due to the Pauli exclusion principle, which simply states that if you have electrons, they're going to spin in opposite directions, something like that, to maintain balance. And the idea here is, again, everything needs to be balanced. So one electron will be spinning this way, other electron spinning this way, and the two of them balance each other out. And then, so as you're filling up, you're going to say, in your 1s, you're going to have electrons spinning this way, electrons spinning this way, 2s, again, opposite directions, 2p, opposite directions, and then as you go through your 3p options, you have opposite directions again. Because you're going to have your orbitals filling up in a particular pattern, and if you look at your wonderful, if you look at your wonderful periodic table, there we go, you're going to see that you can figure out what orbital you're going to using that. So, if you look at, first things first, your top row, your top period is going to have, hydrogen, helium. Hydrogen and helium, both of them will have electrons in your 1s. Then you go down and you're going to just see the 2 left columns, which are going to be your 2 left groups. And those are going to have their outer electrons in s orbitals. Then you're going to see your center block, all of your inner metals, and those are going to have electrons in the d block. Your bottom block, which is, the one that sticks out on the very bottom of your periodic table, kind of separated from everybody else, that's your f block. And then over to the side, you're going to see your p block, and that's where you have your fellows like, aluminum, carbon, oxygen hanging out. That's the cool kids club. So that block, say you see it's 6 wide. So obviously we know that only 2 electrons can occupy a single orbital. So the question is, how can the p orbitals have 6 different electrons in them? Well, it's because p orbitals have 3 different orientations. So you have the p orbital oriented along x-axis, y-axis, and z-axis. And thus, you have your particular p orbitals, 3 p orbitals, but yet you're going to have 6 electrons in p orbitals at this first energy level and second energy level, so on. Okay, so we know our spin, we know our sublevels, and this gets us our sublevels. So you have, if you're calling it, it would be 1s, and you're saying 1s, and that's going to be obviously your 1s orbital, pretty straightforward. What happens when you get to 2p? What do you do then? Because you have these 3 different orientations. You would say 2p2, 2p1, 2p2, 2p3. That doesn't sound right. So that's going to be the number of particular orbitals in that area.
2p.
Oh, 2p6. But yeah, there we go.
2px, 2py, and 2pz.
Yeah.
And 2p fills up to 6.
So it goes all the way up to 6. Woo. And then we have Aufbau principle, which is your orbital diagrams. And all that's going to say is that electrons are placed in lowest energy level first. Pretty straightforward. An electron will be placed in the 1s and the 1s orbital before it goes to the 2p orbital, because they're not going to tend to have energy if it's in the ground state, which means it's not currently energized. Then if you move on, you can say other principles. What happens if you have 2 electrons in 1p orbital block? So if you're looking at the p's and you say we have 2 electrons here, how do they work? Electrons will tend to spread out, so they will be in separate orbitals if possible, because they don't want to be spinning against each other. So then you're going to go 1s1, 1s2. They're going to fill up the 1s, then 2s1, 2s2, and fill up the 2s full. And then you're going to end up at the 2p. And it's going to fill up through the 2p, and it's going to have those 3 orbitals. They're going to fill up the first orbital, 1 electron, second orbital is going to get 1 electron, third orbital is going to get 1 electron, and then it'll go back over with the first orbital getting its second electron, and so on. Because again, the electrons don't want to share that space because negative charges are going to repel each other. Okay, so this moves on to the idea of the relative energy of orbitals depending on atomic number. If you look at your transition metals, and especially your intertransition metals, you notice that a lot of the properties are going to be similar, and this is because of the d and f orbitals. The d and f orbitals, like I said earlier, are lower energy than your s and p orbitals. And all that means is that when you have atoms which only have changes in the number of electrons in d and f orbitals, it's not going to affect valence electron numbers, and therefore is not going to majorly affect how it tends to bond. Okay? And that being said, we've only got a few things left. Electron configuration of ions. We discussed earlier how ions work. How do you configure electrons for ions? Well, an ion will always have an electron configuration, unless it's being weird, of a neutral gas. So a neutral gas will have 8 valence electrons. An ion will have 8 valence electrons. It's going to have either gain or loss electrons to achieve that noble gas configuration. And finally, just a review, when you're looking at your periodic table, you can use it to figure out how exactly you configure things with your S block, D block, P block, and F block. As you go across, you can literally just count up every element that has come before your particular element and say that's how many electrons it has in the S block, and using your periods, of course. If you look at your first period, you could say, okay, hydrogen, helium, it has 2 electrons in the first level of the S block. Boom. Or if you go down, you can then say, okay, lithium, beryllium, and lithium, barium, it has 2, this is beryllium, it has 2 electrons in the second level of the S block, and then that'll allow you to chart out exactly where your electrons are within your atoms. There you go, that's electron configuration and atomic structure. Have fun until next time, and don't remember, you finished the simplest topic, so it only gets harder from here.